Hello and welcome to this video. This is Mr. Clark here. We're going to be covering the topic of energy for physics, particularly energy calculations that you need for your examinations. These are the aims of the lesson. At different points during the lesson, I'll be asking you to pause the video and to have a think about things and to try some calculations for yourself. If you can be ready to do that, that would be great. So we're going to start with being able to recall and use equations to calculate energy in kinetic and gravitational stores. I'd recommend at this point that you watch the other video, which was before this one, Introduction to Energy, which covered the energy stores and transfers model. This is the list of energy stores that we're going to be referring to. But it is covered in more detail in that first video. Quick activity, see if you can remember these equations. So I'd like you to pause the video and try and remember these and write them down. So it's the equation for work done. We did do that in the last video. The equation for kinetic store of energy and the equation for gravitational store of energy. So here we are, check to see if you got these correct. So the first equation, work done equals force times distance, distance moved in the direction of the force. Kinetic store equals a half times the mass times velocity squared. Gravitational store equals mass times gravitational field strength times height. Or you may have gravitational store equals weight times height. That would be equivalent. Well done if you got all of those right. So we're going to be thinking about an example now, throwing a ball up into the air. I'd like you to think about how you could make the ball go higher, and I'd like you to think about this in terms of the energy stores involved and in terms of work done on the ball. What would you have to do to make it go higher? So pause the video and think about that. So to get the ball to a higher height, you may know this from experience of trying to do this. You need to do more work on the ball. That means either a bigger force upwards when you're releasing it, or that force acting over a longer distance. Doing more work on the ball would transfer more energy to it, so it would have more energy in the kinetic store. If it's got more energy in the kinetic store, it can then go to a higher height because it can then transfer more energy to a gravitational store. So all of these ideas would be along the right lines. So we're now going to apply the equation for work done to a situation where we're lifting a mass vertically upwards from the ground. So we're going to lift the mass from the ground up to a height of 1 meter. And you can see there that it's got a mass of 5 kilograms. So we're going to be applying the equation for work done. The general equation for work done is work done equals force times distance. When we're lifting a mass directly upwards, the force is the weight. So what we need to do is find the weight of this mass, and the distance moved is the height gained. So we can find the work done from weight multiplied by height gained. So we're given the mass of 5 kilograms. We need to convert that to a weight. So you may have met this equation before. Weight equals mass times gravitational field strength. So the gravitational field strength value on Earth is 10 newtons per kilogram. It's a rounded value. It's the value you'll be given to use in exam questions. So we simply take the mass, 5 kilograms, and multiply that by 10 newtons per kilogram, and we get a weight of 50 newtons. So what we've then got to do is just take the weight multiplied by the height, so it's 50 times 1, and that gives us a work done of 50 joules. So what does that mean? So 50 joules of energy has been transferred. Work done is equal to the energy transferred, remember. So 50 joules of energy has been transferred, it's shifted between stores. So which store has it gone from, and which store has it gone into? So the ball has gained height above the ground, so there has been some transfer of energy into the gravitational store, and that energy would have come from the chemical store of the woman. So this is to summarize the equations that we've been using. So we started off with the general equation for work done. So work done equals force times distance. What we're saying is the work done is the energy transferred into gravitational store of energy when an object gains height. The force that we need to use to lift it is the weight of the object, and the distance that it needs to move is the change in height above the ground. So from that we then calculated the weight by taking the mass which we were given and multiplying that by the gravitational field strength, and that then gives us this more general equation for gravitational store of energy calculations. So EP is the energy in the gravitational store, is equal to the mass multiplied by gravitational field strength multiplied by height gained or lost. So here's one for you to try. So calculate the energy in the gravitational store when you have a 2 kilogram can of paint at a height of 1.5 meters above the ground. I'd like you to pause the video. I'd like you to have a go at this. I'd like you to show each step of your working clearly and make sure you get the correct units in your answer. So you've got an answer of 30 joules. Well done. So how do we do that? Correct your work if you need to. We're using the equation mass times gravitational field strength times height. So it's 2 kilograms multiplied by 10 newtons per kilogram multiplied by 1.5 meters will give us an answer of 30 joules. So do your corrections if you need to. If you got that all right, then well done. So here are some further questions for you to try. Again, making sure you show each step of your working and making sure that you have converted any units that you need to convert using mass in kilograms and height in meters. You may need to sometimes convert and to show the answer with the correct units. Pause the video and have a go at these. So here are the answers to those shown in red there. So mark your own work and check the units are correct, and well done if you've got all of these right. I'm just going to quickly run through how to do each of these. So the first one is asking for us to calculate the energy in gravitational store. So we're going to take use the equation m times g times h. So it's going to be 2 kilograms times 10 times 2, and that gives us an answer of 40 joules. The second one, just need to be aware on this one that we need to convert the mass into kilograms. So 347 grams is 0.347 kilograms times 10 times 231 gives us our answer of 802 joules. For the third one, we have got just pulling out the values there that we need. We've got a mass of 20, we'll take g as 10, and we've got a height of 2, so that's going to give us 200 times 2, which is 400 joules. And then using a power equation, power equals energy transfer divided by time, so that's going to be 400 divided by 0.5, which is 800 watts. Check your answers, check your working, and well done if you got all of those correct. So some examples shown here of objects which have energy in a kinetic store. So you can probably think of lots of examples of your own, but we're going to be thinking about how to calculate kinetic store of energy. So what do you think it depends on? So the equation for kinetic store is a half times the mass times velocity squared. What would the units be? So any store of energy is going to have the same units, and that unit of energy is the joule. Let's take an example. So we've got the car with a mass of 1,000 kilograms travelling at 10 meters per second. Calculate the kinetic store of energy. So let's see how we arrive at the answer of 50,000 joules. So kinetic energy equals a half times the mass, which is 1,000, times the velocity squared. So it's going to be a half times 1,000 times 100, or it's a half of 100,000, which is 50,000 joules. So we're now going to double the velocity of the car, so it's going from 10 to 20 meters per second, and we're going to calculate the new kinetic store of energy. What would you expect it to be? So the answer is actually 200,000 joules. Let's have a look at how to do that. So using our kinetic energy equation, we've got 0.5 multiplied by the mass, which is still 1,000, multiplied by the new velocity, which is 20 squared. So that gives us 20 squared gives us 400. I'd always do that first. Multiplied by 1,000, multiplied by 0.5. So it's a half of 400,000, which is 200,000 joules. It's interesting to note here that when we double the velocity, the energy in kinetic store doesn't double, but it increases by 4 times. It went from 50,000 to 200,000. And if you think about the equation, you've got the velocity squared, and that's going to mean that it's not a linear relationship. Right, so here's some questions for you to try. So I'd like you to practice using the equation. I'll just write that here to remind you. So energy in a kinetic store is equal to a half times the mass times velocity squared. So for questions 1 and 2, you need to find the energy value. For 3, you've got to find the mass, and then for question 4, you need to find the velocity. So if you could remember to show each step of your working and to write your answer with the correct unit, and be aware of any conversions that you might need to do. For example, mass needs to be in kilograms for the equation to work. So if you'd like to pause the video and have a go at those. So here's the answers. Let's just run through how to do these. So for the first one, using the equation half mv squared, half times 20 kilograms times 15 squared. Multiply this out, you get 2250 joules. For the second one, we just got to be aware that the mass is given here in grams, so that will need to be converted to kilograms. So it's a half times 0.315 kilograms for the mass times 15.8 squared. Multiply that out, get 39.3 joules. Question 3, we're asked to find the mass. So we're going to put the energy on the left hand side, make that equal to half times m, unknown mass, times 5 squared for the velocity. So simplify down to find mass, times both sides by 2, multiply out the 5 squared. So we're going to get m equals 24, 600 divided by 25. And for question 4, we need to find velocity. So it's 4,500 for the energy equals half times 10 times our velocity squared, times both sides by 2, divide both sides by 10, take a square root, and we get V equals 30 meters per second. So well done if you got those correct. Right, here's one to just pause and think about. So the chart shows the total stopping distances of a car at different speeds, and the stopping distance is made up of two components, the thinking distance and the braking distance. The question here is, why is the braking distance so much longer at higher speeds compared to at lower speeds? So work is done by the brakes to transfer energy from a kinetic store. For the car to stop, all of the energy has to be transferred out of the kinetic store. So the work done is equal to the kinetic store of energy. The kinetic store of energy is proportional to the velocity squared. Remember the equation, half mv squared. So as you increase the velocity of the car, there's a non-linear increase in the kinetic store of energy. It increases more rapidly than the velocity, and therefore more energy needs to be transferred, so therefore more work needs to be done. And that helps to explain why the braking distance increases in the way that it does. So we're now going on to think about the equations for the elastic store of energy. When you stretch an elastic band or a spring, you have to do work on it to do that. There has to be a force which moves it a distance, and that energy is transferred to the elastic store. The spring or the rubber band stores energy. The more you stretch it, the more work is done, and so more energy transfers to the elastic store of energy. This is the equation for the elastic store of energy. Elastic store equals 0.5 times spring constant times extension squared. The elastic potential energy is another name for the elastic store of energy, is in units of joules. The spring constant K is in newtons per meter, and the extension E is in meters. So the spring constant tells us how stiff the spring is in newtons per meter. The higher the value, the stiffer the spring. The extension, remember it's the extension and not the total length of the spring that you need to use. The diagram shows a spring extending from its original length to a new length, and it's that change in length which is the measurement of extension. This equation only really works when the limit of proportionality of the spring has not been exceeded. Elastic store equation example. This is a worked example to show you how to do it. So you'll be given this equation in your exams, and it's one that you need to be able to use. To calculate the energy stored by the spring, which extends by 5 centimeters when a mass is added, the spring constant is 10 newtons per meter. So we're going to put the values we've been given into the equation. We're going to remember to convert the centimeters into meters. So 5 centimeters equals 0.05 meters. So put the values into the equation, we get 0.5 times 10 times 0.05 squared. Multiply that out and we get 0.0125 joules as our answer. So a stretched rubber band can be used to catapult a toy car along the floor. This activity is to try changing the amount of stretch and observe the speed of the car. Try that for yourself. How does the speed of the car appear to vary as the elastic band is stretched more? Try and explain what is going on. You may have noticed, if you tried that when stretched further, the car will move off with a faster speed. The explanation is that when stretched further, more energy is stored by the rubber band, so that when released there is more energy transferred to the kinetic store of the car. So we're now going to use the equations that we've been practicing so far, and we're going to apply them to solve problems where energy shifts between stores, e.g. when energy shifts between a gravitational and a kinetic store of energy. Let's just pick up on the toy car activity. So this is an example of elastic to kinetic store, and we can do some calculations with it. So when the elastic band is released, energy transfers from the elastic store of the band to the kinetic store of the car. If there was 0.5 joules of energy stored in the elastic band before release, how much energy will there be in the kinetic store of the car, assuming there are no losses? So the answer is 0.5 joules. So all of that energy that was in the elastic store has now been converted into the kinetic store of the car. Where it says assume no losses, it really means assume that no energy has transferred into any other stores, such as a thermal store due to friction. We can ignore all of that and just assume that all of the energy goes into the kinetic store of the car. Pause and do this. Elastic to kinetic store calculation. If there was 0.03 joules of energy stored in the elastic band before release, calculate the maximum speed of the car, ignoring the effects of friction. The mass of the car is 120 grams. So we will assume that this 0.03 joules of energy has transferred into the kinetic store, and we'll use the equation for the kinetic store to find the velocity of the car. So 0.03 joules is equal to a half times the mass, 0.12 kilograms, times velocity squared. And then we'll rearrange that to find velocity squared and then square root it to find velocity. So we get v squared equals 0.5, so v equals 0.707 or 0.71 meters per second, to two significant figures. So we're now going to look at an example of gravitational to kinetic store transfer. A 5 kilogram ball is dropped from a height of 1 meter above the ground. Calculate energy in the gravitational store before dropping. G equals 10 newtons per kilogram. And calculate the speed of the ball just before landing. Ignore the effects of air resistance. So if you could pause the video and have a go at that. So for the first one, we're using the equation for gravitational store, which is mass times gravitational field strength times the height change. So it's 5 kilograms multiplied by 10 newtons per kilogram multiplied by 1 meter gives us 50 joules. So when the ball is dropped, the energy is transferring as it falls from gravitational store to kinetic store. Just before the ball lands, we assume all of that 50 joules of energy has transferred to the kinetic store of the ball. We are ignoring the effects of air resistance. So we can then use the kinetic equation like we did similarly to the elastic store example. We can say 50 joules is equal to half times the mass times the speed squared, half times 5 times velocity squared. We don't know the speed that we're trying to find. V squared equals 20, so V equals 4.47 meters per second, or 4.5 to two significant figures. So that brings us to the end of the video. I hope you found it helpful. Here's a chance now for you to go back and review your learning. You can watch any of the sections again. If there's anything there that you're less confident with, go back and watch that section of the video again. Otherwise, I hope you found the video helpful, and I look forward to seeing you soon.